Hello and welcome to lesson 9.6 on applying trigonometry. Today we're going to continue on our topic of trigonometry and see some real-world problems, try to solve them by using trigonometric ratios and their inverses. We're also going to try to derive and use a formula for the area of a triangle by using trigonometry. So those are kind of the two goals of this lesson. There are a few vocab terms we're going to learn: indirect measurement, angle of elevation, and angle of depression. So before we get to that, I want to kind of take a step back and just talk about trigonometry in general, um, sort of build up the general idea of the study. So trigonometry has a lot to do with the ratios of the sides of a triangle. So for example, with this angle as our reference point, we're going to name the three sides: the opposite side, the adjacent side, and the hypotenuse. The hypotenuse, as we know, is the longest side of the triangle. The adjacent side will be whichever side is touching the angle that is not the hypotenuse, and the opposite side will be the side that's straight across from the angle. Okay, so with those three things in mind, there's three different comparisons we can make. We can ask, how does the opposite side compare to the hypotenuse? How does the adjacent side compare to the hypotenuse? Or how does the opposite side compare to the adjacent? Those three comparisons are giving three vocabulary terms: the word sine, cosine, and tangent. So if I ask you to tell me what is the sine of this angle, what I'm really asking you to tell me is how much smaller is the opposite side than the hypotenuse? Like, what is the proportion between these two sides? Is it 1 to 2? Kind of based off the picture, that's what I would imagine this would be. So like this could be 1, this could be 2, or this could be 10 over 20. Either way, the ratio would be 1 to 2. Let's take a look at some of those special right triangles that we've seen before. So for example, for like a 30-degree angle. Yeah, so if that was a 30-degree angle that we looked in the last picture, it would be a 1 to 2 ratio. So they're giving this as a variable. But let's imagine this variable is 1 right now. Let's call this h(1). So this side is 1, this side is 1/2, and this side is square root of 3/2. Well, if I ask for the sine of 30 degrees, that would be opposite, so straight across, it'd be 1/2 divided by hypotenuse, divided by 1. So 1/2 over 1. Okay, 1/2 divided by 1 is 1/2. So we would say that the sine of 30 degrees is 1/2. That means that when you have a 30-degree angle, your opposite side will be half as big as the hypotenuse. Okay, so when people began working with this idea, they would do that for various triangles. So they would do it with a 30 degree, they would do it with 45. So for a 45 degrees, we'd say the sine of 45 is going to be opposite over hypotenuse. Let's call these k's 1 again. So 1, 1, and square root of 2. So the sine of 45 would be 1 over the square root of 2. Okay, so that would be the ratio between those two sides. Now, those are harder and harder to know if we have angles that are in between. So let's say we have like a 31-degree angle or even a 31.5-degree angle. Well, we only know these sides because these were a special case where we could figure out the side lengths. Sometimes the side lengths are not as easy to figure out. So what would have been done is people would have started out by literally just measuring these, like get a ruler out and measure this side and measure that side, and then find their ratio, divide one by the other, and they'd say that that answer, the quotient that you got when you did that division, was your sine value. And you could go through and you could do this, and you could figure out all the different values that would be possible and kind of make a table that would be kind of like a booklet full of answers to those questions. So this one's listing cosine, which is a comparison between the adjacent and the hypotenuse. So this one says that when you go through and you measure a 0-degree angle, the cosine is 1. When you measure a 1-degree angle, so just a tiny little 1-degree angle, the ratio between the adjacent and the hypotenuse is 0.99. Okay, so that means that the adjacent side is 99% as big as the hypotenuse when you only have a 1-degree angle. That would kind of make sense because if we're doing a right triangle, we have opposite, hypotenuse, and adjacent. cosine is comparing your adjacent to your hypotenuse. Well, if you only have a 1-degree angle, if you got like this really, really, really skinny angle, the hypotenuse is always going to be longer than the other two sides. But if we only have a 1-degree angle, it's not going to be much longer, right? They're getting pretty close. The closer we get to 0, the closer we get to two lines that are just going to be directly on top of each other and are going to be the same length. That's why the ratio between them is 1 when we have an angle of 0. As the angle increases, the bottom side is about 99% as big as the top, then less and less and less. Eventually, we get to the point where, let's go to a 45-degree angle. Okay, so at a 45-degree angle, they're saying the cosine is, I'm not sure why they have commas here, don't worry about that, is 0.7. Okay, so if I have a 45-degree angle, something like that, they're saying that whatever this is, if this is 10, then this side is about 7. Okay, it's 70% as big as the top. That's what this measurement is telling us, the ratio between these two numbers. Okay, so if I did adjacent over hypotenuse, 7 over 10, I would get, roughly 0.7, like they're saying on the chart. Okay, so people would go through and they'd do those measurements, and they would assemble these tables. These would just be called like trigonometry tables. And then whenever you had a problem, so for example, whenever you were doing something like somebody is, I don't know, they're constructing the pyramids, they have an idea of the angle they want to build at, they want to know how, tall they're going to get to if they want to have a certain length along the bottom, say something like that. So we want to have a pyramid. We know we want to be like 1 mile wide. We know we want to go up at this angle, and they're curious, how tall is that going to be, right? They haven't made it yet, they can't measure it yet, but they do know the angle, and they do know, or let's say it's 2 miles wide, that'll make it easier for me right now. They do know how far across it should be, right, like that. So they're trying to just figure out, what is the height going to be? Well, if you know the angle, if you know 45 degrees, and you know the length of one of your sides, all you need is the angle and one side. And with trigonometry, you can figure out the rest. So we would go to our table, we'd say, okay, we want opposite over adjacent. So we would not go to a cosine table. We would go to a tangent table. We'd go to a booklet that had been filled out with different tangent values for different angles. And we'd say, okay, well, what is the tangent of 45 degrees? What is the tangent of 45 degrees? And if that problem had already been done, so somebody else had already taken a 45-degree triangle of some other size, okay, it doesn't need to be as big as a pyramid, it can be as small as the picture I'm drawing, right? Because all 45-degree angle triangles are similar triangles. So for example, if this is 2 and this is 1, then the larger triangle could be something like, 4 overall and 2 overall. They're going to have the same proportions. Smaller and larger similar triangles will. Okay, so you turn to your book of tangent values. You'd figure out what this is. So I think the tangent of 45 degrees, if I'm not mistaken, should just be 1. Okay, then you'd say, okay, well, if this is a mile in length, excuse me, then this is going to be a mile in height. Okay, and that would be kind of an application of trigonometry. But to say what I said just a moment ago, an important idea in trigonometry is that if you know an angle, if you know what this angle is, and you know one side, all you need is one side. If you know an angle and one length, wherever it is, doesn't matter, you will be able to figure out the other two lengths and the other two angles. Okay, so you only need 2 pieces of information in a triangle once you understand trigonometry to fully fill out all the details of the whole triangle. Now, this subject goes in some interesting directions. So as I've said before, trigonometry is incredibly connected to the subject of circles, as it turns out. Now, I'm not going to talk my way through this whole thing because this is a big topic that you'll do in a future class in like Algebra 2 classes, but I just want to give a little preview here. So if we think about a circle whose radius is 1, so when I say the radius is 1, this gray line is 1, right? It's just 1 unit long. Well, then these ratios, like sine, for example, opposite over hypotenuse. The opposite of this angle would be the green line on the triangle, and the hypotenuse is 1. So you'd be putting like 0.74 divided by 1. Well, the divided by 1 doesn't really change anything, so this is why the circle being a radius of 1 is kind of helpful. So the sine is just whatever the value next to the green line is. So as I go around this circle, I'm being told the sine of different angles. So I don't think I can turn off individual ones. So ignore on the right side over here, ignore the gray part, ignore the blue part, just look at the green part. Okay, this kind of wave that goes up, down, and up. So they're saying the sine of 0 degrees is 0. The sine of 60 degrees looks like 0.8. Oh, sorry, not 60 degrees. I'm looking at the wrong part. Sine of 53 degrees, if you look up here at the top. Sine of 51 degrees is 0.7. Sine of 70 degrees is 0.9. Sine of 90 degrees is 1. Okay. If you chart all of these sine values, like if you took all of these values and put them on a graph to see what they're doing over time, what they are doing over time is they are creating a wave. Okay, they're creating a measurement that's going up, coming down, going up, but not in straight lines, in these kind of smooth curved lines. Now, these waves show up all the time in nature. One place that I love to connect them to is to music. So if you have a guitar and you like film it in slow motion, what each different string is doing is it's vibrating in a wave pattern of different wavelength. So some of the waves are really close, some of the waves are wider. The lowest notes are going to have the kind of widest waves, and the high pitched notes are going to have really skinny little close waves. Okay, so you're going to get things like this in music. You also get things like this if you just record someone talking. So if you, not sure where you'd see this kind of readout, but like if somebody is recording some kind of voice, this is typically what you see. If you're recording music, this is what you see. And the reason for that is because the way that our voice and the way that musical instruments make noise is by vibrating the air, by pushing it back and forth. And those vibrations reach your ear and vibrate your ear. So anything to do with the vibrations, which is like noises, light traveling through the air, things, oscillating on strings, atoms bouncing back and forth, all sorts of things in the world. And actually, if you get far enough into science, you find out that almost everything in the world is a description of things oscillating, of things kind of vibrating around. Like, for example, like measurements of heat often have to do with how things are wiggling around. So these vibrating motions are created by putting together different waves. So like we can have a function that's the sine of x, and it'll make a wave. And we can change that into different waves by kind of messing around with the function. So I can make the waves really short. I can make the waves bigger. I can move them around. I can kind of shift them around. See, um, I can kind of shift them left or right. This is kind of where the eventual applications of trigonometry go. So we will not be seeing this, like I said, we will not be seeing the wave parts of trigonometry, but I do want you to understand that when you're studying trigonometry, you're studying something that connects to a whole lot of things outside of geometry. If like as I said before, if Pythagorean theorem is one of the most essential things to understand within geometry, trigonometry is one of the most essential things to move concepts out of geometry and connect them to all sorts of other topics in the world. Okay, so that's kind of the general pitch on what trigonometry is all about. We're going to be doing simpler stuff today. We're just going to be working with these these vocabulary terms, sine, cosine, and tangent. And we're going to be kind of solving for missing sides on a triangle, missing angles, that sort of thing. So filling out the information that we can get based off using these. We won't be using a table. we'll be using a calculator, so we won't be finding these values by hand. Although, like I said, you could if you just had a ruler and you measured them. But we will be using a calculator. Calculators, sometimes they just kind of have tables programmed in that they reference. Other times they might do certain calculations that are sort of advanced calculus calculations in order to find them on their own without having like pre-measured them beforehand. But that stuff is a little farther out than we're going to work on right now. What we're going to work on right now, we're going to use calculators. We're going to use kind of like pre-known values for these different cosines, sines, and tangents in order to solve problems. So in our first problem, they want us to work with something called angle of elevation. So they say that Rakim is flying his drone at the park. He spots the drone at an angle of elevation he estimates to be 30 degrees. Angle of elevation just means the angle upward. So if you're looking at like the top of a mountain, the angle from the ground up to the top of the mountain is your angle of elevation. If you're on top of the mountain and you're looking down at, Yakima or something, you're on top of Mount Adams and you're looking down at Yakima, that would be an angle of depression. So there's those two different words, elevation and depression. Elevation meaning looking up, depression meaning looking down. So he estimates the angle to be 30 degrees. The remote control tells Rakim that his drone is 102 feet above the ground. He is 6 feet tall. How far is he away from the drone? So how far away is AB? Well, because Rakim's 6 feet tall, we can take that away from 102, and we can say that BC would be 96 feet. Okay, so let me look at that. So we have a 30-degree triangle here. It is 96 in that direction. It is 30 degrees here. So if we were going to use one of our three functions, the function we'd need to use would be, we're trying to figure out this length here. So we really want the one that's connecting the opposite side to the hypotenuse. So O and H. Well, that is our sine, right? Sine is opposite over hypotenuse. The way that people memorize those is they memorize this kind of phrase on the bottom, SOHCAHTOA. SOHCAHTOA. That's what we'll say. SOHCAHTOA is how we'll remember. So is sine is opposite over hypotenuse. Ka is cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. SOHCAHTOA. So we're doing the so part, SOH. Okay, so the sine of this angle, the sine of 30 degrees, equals the opposite side, 96, over x. Okay, we're trying to find x. Now, if we want to do a little algebra right here, I could multiply both sides by x to get x sine 30 equals 96. And I could divide both sides by sine of 30 to get x by itself. You want to think of this whole thing as like one chunk, so that will never get separated. You wouldn't divide by 30 or something. This is an operation that's happening to the number 30, so it kind of all sticks together. Okay, so we can do that if we want. Now we don't have to. We could have at this stage figured out what sine of 30 was first and went from there. But I just kind of went ahead and moved it all so that we've got x by itself. So this is going to be our answer. Now they're probably not going to want this. They're going to want us to simplify what sine of 30 is. This is the point at which somebody would have went to like a table and went, okay, the angle is 30. What is the sine? Well, this is a cosine table. We're not going to use that. What we're actually just going to use is a calculator. So we're going to say sine of 30 degrees. What is that ratio? Well, the ratio for the sine of 30 degrees, you have to type in degrees. Be careful here because there is something called radians. Radians are like an alternate unit to degrees. There's 360 degrees in a circle, and there's 2 pi radians. It's like a different measurement type, just like feet and meters are measuring the same thing. They're both measuring lengths, but they are not the same length as each other. Like a foot is smaller than a meter. Well, a radian is larger than a degree. But we're going to work with degrees. So you want to make sure you type in degrees, or else they might give you a wrong answer. They typically, when you just type it in, will think you're talking about radians. There's reasons you'll learn next year why that's kind of a more useful number system to work with. But for now, we want to do degrees, so we'll type that in. Okay, so they're saying the sine of 30 degrees is 0.5. So back to our picture, that means that when we have a 30-degree angle, opposite over hypotenuse equals 1/2. Okay, so there's a 1 to 2 ratio. Whatever this is 2 times as big, okay, in a 30-degree angle here. Okay, so if this was 10, this would have been 20. And if this is 100, this is going to be 200. Well, in our case, this side is 96, and this side is going to have to be twice as big as that. So like 192. Okay, so at this stage, we would have replaced sine of 30 with 0.5, and that would have simplified to be 192. Okay, and that is the process you'd go through to use trigonometry to solve for a missing piece of a triangle. Okay, kind of going back to our first point, which was saying that in trigonometry, all we ever need is one side and one angle, and we should always be able to figure out all the other information on the triangle. All right, excellent. So we will take a look at example number 2 in the next video.